We asked you to couple the names of various techniques to the circuits that you saw. And we understand that this is maybe a, let's say, difficult thing to do at this moment, but it gives us a lot of information about how we are looking to circuits and maybe also to designing. So what we'd like to have at the end of the course is that you know about design methods rather than circuit solutions. With design methods, if you have methods, you can generate a lot of solutions yourself. If you only know a limited number of solutions, you are stick to that number of solutions. So that's why we ask you to see if you recognize techniques or methods in the circuits. So let's start with what is brute force? What is a brute force technique? A brute force technique is a technique in which you fix a relation between a branch voltage and a current simply by inserting that relation there with a device like a nonlinear resistor or a resistor or whatever. That is called brute force. What is compensation? Compensation is that you reproduce an error that somewhere occurs in the system, and at that place somewhere you add it with the opposite side. So you subtract it from the signal, and then you compensate basically for the error. It's an additive technique in this way. Negative feedback. Well, we have dealt with negative feedback in the bachelor course already, so I suppose that you know what negative feedback is. You measure the response, you compare it with a desired value, and you somehow nullify the difference between what you desired and what you have got. So that is negative feedback. Now let's have an investigation of those techniques on the circuits. So let's start with the brute force. We know from the bachelor course, from structured electronic design, that insertion of impedances in a series of or in parallel with the signal path should be avoided. Usually you get a deterioration of the signal to noise ratio, of the noise performance. You have an increase of power dissipation or an increase of energy storage, and maybe resulting in deterioration of the overdrive recovery. So let's see in the circuit, and here I have some circuit, just picked up one from the examples. Where do we speak of brute force? Well, basically here we fix the gate to a certain voltage, but by just tying it to this voltage, but let's say this resistor is in parallel with the signal path. This is assumed to be a kind of voltage reference, and this is tied to a voltage reference so that we get the voltage at the gate. But if we make the resistor very small, it will of course influence the transfer here, but it will also evoke a noise current, a large noise current in parallel with the signal path. Another place. Here we wanted to have a current source, the bias source, but in the current source, the voltage and the current are orthogonal. So there's no relation between voltage and currents across an ideal current source. So we could not fix the voltage here with simply placing a current source there, unless for one particular situation, one transistor and one temperature. That is how we introduced this whole method of biasing. But if the temperature changes, or if you put another device in it, then it might need a different value. So this is a way of brute forcing it. If the value is not deviating that much, then the resistor breaks the orthogonality between voltage and current, and you fix the voltage here. That's a brute force technique. But this resistor, since this is the output, is in parallel with the signal path, and it increases the power dissipation. The AC coupling itself is also a kind of brute force technique. Maybe you remember that when I introduced this AC coupling and there was a source connected to here, we said, well, if you power up the amplifier, then these capacitors first have to charge, and this one has to charge. And when this is charging, this capacitor, basically the voltage is not yet good. So the device is not yet biased in the correct way, and the amplifier is not working. That's a kind of startup behavior. Similar things occur when you overdrive it. When you put a very high voltage on here, then this one starts changing the average charge, and you get overdrive recovery. So here you see all kind of brute force techniques in the circuit, and now you can maybe recognize them also in others. And they deteriorate usually startup behavior, overdrive behavior, power dissipation, noise performance. It doesn't mean you cannot do it, but you have to be aware of the penalty that you pay. And if you cannot allow such a penalty, you need to have a better technique. That's the reason. So, of course, we say insertion of impedances should be avoided, but usually you cannot at all avoid it in all cases. And then we have to be aware of the errors and design it such that the errors are small enough. Let's go to the model-based biasing. That was another keyword. Model-based biasing is basically the same as compensation. So if you see compensation, basically because you reproduce an error somewhere with compensation, you use a model for that. And so the application of compensation, it requires reproduction of an error. So if we don't reproduce it correctly, then there will be another error left. And it has limited improvement due to that. So here we have the same circuit, and now where are we doing such a thing? Well, this transistor needs the gate source voltage needs to change with temperature, for example, if we want to maintain the same current over different values of temperature. So how can we do that? Well, if we have some tracking mechanism, if we can put a current through a device, and that is a identical device as this one, let's say good enough, then the temperature change here, the gate source voltage, will be the same as we need there for the current. So we basically copy here the current in this branch from the reference that we have here. So that is a kind of compensation technique that we have. And it is, of course, limited to the matching of the two transistors that we have in this circuit. So the next one is feedback biasing. I don't want to jump immediately to the circuit, but maybe tell you a little bit more about feedback biasing. It's an error reduction technique. It automatically reduces errors due to biasing because we have a reference. But it is only possible if the frequency components of the biasing, the bias errors, and the signal do not overlap in the frequency domain. Let's say if you are interested in frequencies of 1 millihertz and your temperature changes have the same frequency, then you cannot make a distinguish between your noise coming from the temperature changes, basically such a temperature error could be regarded to as noise, and your signal that you are interested in. So it requires a loop filter to make a distinction between this is the signal that we want to amplify and this is what we want to maintain as good as possible, zero output or whatever. Let's look at the circuit here. Here we have this transistor biased, but if the temperature changes or if you put a little bit different device in it, it needs another VGS, it needs another current. So the VGS is not a point because we have the capacitors, but it needs maybe another point to have exactly the good voltage here. So what we do is we measure the output voltage. We measure the DC output voltage and we compare it with the desired value, which is here in this case VDS, just the name, can be 1 volt or whatever. And with this difference, we control a current source here. If it drops the voltage, then we control this one so that it gives less current so that it rises again, etc. Negative feedback. And as you see, there's a filter, 1 over S, and a gain. And you can design the gain such that the frequency response is as desired. But we have already, if you would connect this to the source and this to the load, you have already a system with 3 poles then, because there would be 1 capacitor, a second capacitor, and here an integrating transfer. So stability has been dealt with. We have discussed such a circuit with operational amplifiers in the bachelor course, and that is in the homologation program. So this is a way of fixing here the DC voltage at the drain by making a loop with this voltage. Of course, you can do another with this current, sorry. Of course, you could have done it in another way as well. Here, for example, I used the biasing with, I just tie the gate to some kind of reference voltage, and I control this voltage so that the current will be so that the voltage here is exactly VDS. So here I have another type of feedback. And there's another one here in which I control here with this current source. So now that is a nice thing to talk about, because here in the first two solutions, I fix the current to a desired value with a current source, and I control at the input of the device so that the current will be okay and the voltage will be okay. And here in the second one, I fix the current here with a fixed independent current source, and I measure the error and control some voltage that the voltage will be okay here. But here, I don't fix the current. I fix the voltage here, and whatever current I need for that will flow. So if you talk in terms about feedback, you would call this more an overall feedback technique. The transistor is in the loop. Here the transistor is in the loop, and here the transistor is not at all in the loop. You're just fixing the voltage here. So even if the transistor is dead, you would fix the voltage here. So from point that is very important for biasing, for point of testability, here, if there's something wrong with your amplifier, something wrong with the transistor, you immediately have the wrong bias solution, because the controller cannot work because the transistor is part of the loop. In this case also, because the transistor is part of the loop, all of the transistor, you will immediately detect it with a DC voltage here. So the operating point is then, a correct operating point is then telling you that your amplifier will probably work. But here, the correct operating point is not telling you that the amplifier will work, because this control loop is local. So if this transistor is not biased correctly, if this range, of course, is large enough, can still produce the correct voltage. This is a local feedback loop, and this you would call overall feedback biasing. Overall, because the transistor is involved, and here the transistor is not involved. So if I would classify the techniques here, I would say I'd rather have overall feedback, because that gives me a better measure for if my complete circuit is in a good operating point, and not only if the voltage is fixed at a good value. Now let's go to the keyword that no one of you recognized in the circuit. And of course, we can understand this. This is not a big deal. You can view upon circuits in different ways. And for this, we have a little poll also, so that we let you understand how this electronic self-inductance works. So what is a self-inductance? Well, at low frequencies, we have a low impedance. And in this case, we will put a low impedance in parallel with the signal path. And at high frequencies, we want to place a high. This impedance should be a high. And this high frequency should be the frequencies of interest. And the low frequencies should be the bias noise, the bias deviation because of temperature, etc. So we have a question here. And Chris will roll up the poll, I guess. And the question is, what is the output impedance of this circuit?
So we have about 75% still
running out.
So let's have a look.
Okay, we have about 50%, 48% saying R, but we have a lot of people who think it is 1 over GM, and also some who think it's infinite or even undetermined. Well, infinite, I would say I always see a resistance. So if I look the output, sorry, maybe I should have put this picture. If I look at the output impedance here, then I always have a resistor to ground. So it must at least be R. And you see, this is a voltage controlled current source, but there's nothing to control because the input is shorted, so the voltage is 0. It means that this GM is just not doing anything. There's no current flowing. So the output impedance here is simply R. Now let's go to another situation. Let's remove the short at the input and pose the same question. What is now the output impedance?
So we have 82% votes, even more. So I'll close the poll. Let's have a look.
So 50% of the people say 1 over GM, which is the correct answer. Let's have a look how it works. The output impedance is measured by putting a current in it, and then measuring the voltage. And then the ratio of the voltage and the current you put in is the output impedance. So if you put in a current, then this voltage starts to rise, and this will generate a current GM times that voltage, which means that the ratio between the current, here's no current flowing in the resistor, so the ratio between this current and the voltage is 1 over GM. So the output impedance is 1 over GM in this case. So you see the same circuit. If I short it, I have R, and if I leave it open, I have 1 over GM, which means if R is much larger than 1 over GM, and I go from short to open, I would go from a high resistance to a low one. So if I short it for high frequencies, I have at high frequencies R, and at low frequencies 1 over GM. So the output impedance of this circuit would look like this. It would start for low frequencies at 1 over GM, and if R is much larger than 1 over GM, it ends up in higher frequencies at R. Of course, I have no output impedance here, but that's just, to make it a simple circuit. And this is then the expression. You don't need to do any calculation for this, like slide cap or whatever. You just say, okay, if there is no S, that's DC, there must be 1 over GM. So, and if there is the limit for S goes to infinity, there must be R. So you put 1 plus S times something here, and 1 plus S times something there, and you can just fill in the components from GM and R, and you have to add C because S times RC should be, the dimension of the curve should be correct in the numerator and the denominator. So this is, in this region, you could call this device a self-inductance. The zero, it has a lower frequency than the pole if R is much larger than 1 over Gm. So here we can speak of an electronic self-inductance. Go to our circuit and say, well, if I replace this controlled source with a FET, which is basically a voltage controlled current source, and I bias it in some point, so now it will be VGS here, and there will be some current flowing, which is this current, then this behaves in some region like an electronic self-inductance. And of course, it's also feedback, because I have the output voltage here, and I feed it back to the input and have a low-pass filter. So both the keywords, negative feedback and electronic self-inductance, would apply to such a network.